We can go ahead and start the meeting. I would like to welcome everyone to our inaugural seminar series for our AIM Deep program. As most of you probably know, AIM Deep stands for Artificial Intelligence, Machine Learning, and Data Analytics for Energy Exploration and Production. So before we introduce the speaker, basically, I will let my colleague to introduce the speaker soon. But before we do that, since some of you may not be fully aware of what's happening, what is AIM Deep, I will just give a couple of minutes of general overview, and then I'll hand it to Dr. Thakur to introduce the speaker. Basically, AIM Deep is an effort that we started about a year ago. And we have several areas of research that we have been focusing on. We have a strategic advisory board. Some of them are here in the meeting. And some of them are, also we have a technical advisory board. We have several members already committed, and few members are in the process of becoming signed up. So aside from that, of course, our members include Saudi Aramco, Occidental Petroleum, NEC, and Petrolearn. Actually, we have basically people from those companies here today, either in person or remotely. We also have, we call it AIM Deep academic partners, and different other departments that are working with us at the University of Houston. We also have people outside University of Houston, like USC and University of North Dakota. As a matter of fact, I noticed that we have at least a couple of people from University of North Dakota have joined us. Aside from that, we have, we call it AIM Deep vendor partners, and they are here and they will be working with us in some of the projects that we might be involved in. And of course, AIM Deep has several people at universities. Some of our faculty have been working with us. We also have several consultants outside university have been working with us. So we have a good group of people that we are going to focus on several important activities. One of our activities actually is, we call it AIM Deep Seminar Series. And this is a list of current speakers. The first speaker, of course, is Dr. Uchenna. But these are every second or third Monday of every month. We have other speakers from different entities within that structure I told you about. So, and of course, we have this website that you can go. You probably have seen the announcement for Dr. Odi in the website, but hopefully we'll be communicating with you. One more thing, Dr. Odi has agreed. We basically tape this presentation. So those of your colleagues that are missing this meeting, they can access the presentation. And you can also, of course, yourself want to review the material. You will have access to this presentation. So with that, I will hand it over to Dr. Ganesh Thakur, who is one of our, of course, academic partners, but also he is past SPE president as well as past vice president of Chevron. Dr. Thakur?
Great. Thank you, Dr. Fred. It's a great pleasure for me to introduce today's speaker, Dr. Odi. Dr. Odi has his bachelor's degree from Oklahoma University and master's and PhD from Texas A&M University. And he's worked for Devon Energy and now working for Aramco Services. And his background and especially his topic today is of great interest to me and a great interest to the audience also. So I'm looking forward to a great presentation from Dr. Odi, and Dr. Odi is sure the audience will have some good questions for you. And I was reading your abstract. It is full of great ideas. So ladies and gentlemen, let's welcome Dr. Odi to our first talk for MD. And Dr. Odi, we are glad to have you, sir, here. Thank you so much for coming. Great.
Thank you,
have a great talk. Thank you.
Thank you, Professor. I'd like to begin and just say thank you for inviting me. On behalf
Can
of
you put the slides on the Zoom so that remote people can see it also? I guess, okay.
Okay, do you see it?
Yeah, that's good. And maybe you can make a presentation mode. Good, good, fantastic.
So I'd like to just thank you for inviting me here. This is, believe it or not, this is the first presentation I've done in a while due to COVID. So just happy to be back doing this sort of thing in the industry. This is the topic of what I'm going to discuss today: applied transfer learning for production forecasting in shale reservoirs. Now, the last couple of years, I've seen different approaches to this. And so I think this is still an ongoing effort to fully understand the best way to implement transfer learning. If you are familiar with big data, the Googles, the Facebooks, the Netflix, and etc., a lot of effort to understand how to use transfer learning is geared towards visual AI, computer vision. But a lot of times we're interested in essentially predicting a number instead of predicting a sort of picture. So with this talk, I hope it can kind of lay a foundation for discussion, and then we can kind of discuss further ways to improve the workflow. I did have preloaded into Spotfire the results of this work. I was really happy with the work, illustrating the approach applied to over 20,000 wells in Eagle Ford. But unfortunately, I can't really bring those results out of my work machine. And so, but if later the students here want to see it and we can have a discussion, I can kind of show you those results and we can discuss ways to improve it. Because I know you guys are really geared towards research, and where my role at Aramco America is more interested in operations, really just applying new ideas. So this is an overview of my talk today. I'm going to go through a problem statement. Then I'm going to discuss transfer learning. I'm going to go through the simulator assumptions, because I did use a simulator to generate synthetic data. Then I'm going to discuss inverse modeling using machine learning, then transfer learning for half fracture length prediction, then transfer learning for gas production rate prediction. Then I'll go through some conclusions and then recommendations for future work. So this is the problem statement. So why use transfer learning? The main reason I think that we should be using transfer learning for shale data is because the production history is so short. And in addition to this, a lot of times the physics are not so clear. If you spend your time in conventional fields, of course, we understand Darcy's law works. But a lot of times there are other things in play in unconventional. You have parent-child behavior, you have frag bashing, you have rapid choke changes, right? And so a lot of these things provide challenges in trying to predict rates or predict other things going on in unconventionals. In addition to this, there's also a cost of information hurdle. If you want to gather information by drilling a new well, you have to justify that, right? Is it worth it, right? A lot of times you try to create a science well, sometimes that well doesn't really produce anything, really. And there's a cost of information impact right there, which adds to the G&G cost. So with this work, what I hope to demonstrate is how to estimate half fracture length using a prototype approach, and then also predicting shale gas production. So to kind of just let everyone know, as I was explaining to some of the students here, in my role at Aramco Americas, I generally generate prototypes. And I generate these prototypes based on US production data. And then from there, then, if my counterparts in Saudi Aramco are interested in these prototypes, we help them apply these prototypes to their data. So this is an example of a prototype that I developed. That's a little bit lag. Okay. So just kind of going through an overview of transfer learning. All of us like cars, fast cars, right? Right. So this is kind of going beyond the standard predict a cat or predict a dog, right? And so I mentioned earlier that big data has really generated a lot of work towards transfer learning. In fact, some of the more popular models, deep learning models like Inception and VG16 and et cetera, these models are geared towards predicting different categories of pictures, right? So as an example, just to kind of illustrate what is transfer learning, say that you train a model to predict what a car is, right? The model can look at a picture of a car and say, okay, this is going to be a car, right? In the same token, you have all this data for a car. At the same time, you have limited information for a truck. And the challenge is to develop a model to predict what is a truck. But your training set for a truck is not as rich as your training set for a car. Therefore, you can use transfer learning. The previous model has been trained on a car and then apply that model to predict what a truck is. So this is kind of like a basic example of transfer learning. Now to get into more detail of what is transfer learning, consider two domains, A and B. Now traditional machine deep learning trains domains A and B separately, right? So as this cartoon illustrates, you have model A, you want to train a model. So in our example, model A is trained to understand what a car is, right? And then model B, if we have more data for a truck, we can train a model to predict what a truck is. Now, transfer learning uses the knowledge gained from training domain A to model domain B, right? So in this example that I described earlier, we now have this rich information of what a car is. We train a model and it's able to predict what a car is. Now, in the same token, our data and our understanding of what a truck is very sparse. Therefore, we can take our learnings of what we developed to understand what a car is, our deep learning model, and apply it to predict what a truck is. So then specifically, transfer learning is learning the target conditional probability distribution in a target domain D to T by using the information trained from source task T's of S and the domain of S, DS. So that's really the technical definition of what is transfer learning. And so this is the generalized overview of what I'm going to be accomplishing in this talk. My general workflow for transfer learning, where I'm going to collect source domain data, then I'm going to train a machine or deep learning model using source domain data. Then I'm going to collect target task input data, which is going to be our sparse data set. And then I'm going to apply the model that was used to train that rich data set to the task data set. And so that now we can accomplish transfer learning that way. And I think this is extremely relevant in shale. So before we begin and go through examples of transfer learning, I want to discuss the simulator that I used to generate synthetic data. We developed a simulator in-house within Aramco Americas that models the hydraulic fracturing process. And it's just a basic simulator. It models fracture performance from a horizontal well, as this cartoon illustrates. And the main assumptions for this simulator is that we're modeling interference between fractures. And then also we have the assumptions of infinite conductivity fractures, fully penetrating fractures. The flow is controlled by specifying surface pressures or bottom hole pressures. And then also it's modeling effective flow. I'm not going to model multi-phase flow, but effective flow. And then of course we have different correlations describing some of the PBT in the system. And so there is a corresponding technical paper that describes all the assumptions for this simulator. I can share this paper with you. It was written a couple of years ago, but I can share that with you. To kind of test out the simulator, just to kind of as a sort of a check of the physics, made some different plots. And so this is a legend of what the simulator sees. This is an overview view of the fracture system. X of F represents the half fracture length, and is bounded by a grid of XE width and YE height, but it's looking straight down in terms of the area of point of view. And of course, it has a wub or length corresponding to L to W, corresponding to horizontal well length. So just as an example, generate some example conditions for this hydraulic fracturing simulator. And then just made some plots. And so this is just more of a check to see if it makes sense, right? So before you actually do any sort of data science and machine learning work, you have to make sure that the physics makes sense, right? So this is really my check of doing that. So now with that understanding, I use the process of Monte Carlo to generate sensitivities around this hydraulic fracturing simulator. And the reason why I did this was because I want to see if I can develop a machine learning model for a half fracture length, which is the end goal. So as a sort prototype, I used 350 experiments, and I generated realizations according to these experiments, and I ran each of these realizations. And so these are some of the parameters that I use for these 350 realizations as a sort of a short study of creating a sort of training set for machine learning. And so one of the assumptions with this work is that as I generated these different realizations, the well is centered such that the bounds is very, very large. So it's not going to be impacted by the boundaries of the system. I want to make sure to model the actual fracture performance in the system. And then also I made an assumption that just for now that the composition is constant. For this prototype, this short study, I wanted to illustrate the possibility of using machine learning. And then finally, once I ran each of these realizations, I wanted to look at predicting half fracture length with 1 month of production history, 3 months of production history, 6 months production history, 1 year production history, and then 5 years of production history. And really what my goal is to understand the error through time for the different cases of trying to predict half fracture length with varying amounts of production history. So before I do this, just as a check, I wanted to see if I can model this simulator using machine learning. So as an example, for about 2,000 months of production data, I wanted to see if I can use machine learning to model gas production as a function of time, lateral length, half fracture length, number of stages, permeability, porosity, and net pay. And then from that, I generated a feature impact. And of course, time is very important when you're modeling production rate. Hence, decline curves, right? Or type curves that we use in industry. And then with that, I made a comparison between the predicted and actual, and just looking at the validation, cross-validation, and the holdout, you can see that it does very well in predicting the gas rate. Now, the thing about this is that I did not show you the training set error. I'm not so interested in the training set error. I want to see how well it does with out of bag or the test data set. That's why I kind of show you these results. But just know that those results are okay also. So with that understanding, I then asked myself this question: can I now solve an inverse problem? Essentially, can I predict the state of a system, which in this example is going to be half fracture length, if I know the production history? So I set this problem to do that for 1 month of production history. And as you see here, as this example, just doing the feature impact calculation again, you see the different drivers for this half fracture length. And this is again, using the Monte Carlo study that I showed you earlier as a sort of training set. And so, but one thing that I found very interesting when I plotted the results, initially I was somewhat surprised and disappointed in the results because of the band of uncertainty in production histories. So each of these corresponds to a different realization. But one essential tendency of that prediction, I found something very, very positive and very interesting in the sense that if you look at the central tendency of the prediction, it bodes very well to the actual half fracture length, right? So I using that information, I've repeated the same process now for 3 months of production history, and it provided the same story. But as I went from 1 month to 3 months, the error increased, right? So that's a consequence of kind of increasing the amount of time between, I guess, possibly training the model, right? From 1 month to 3 months. And I repeat the same story for 6 months, and I repeat the same story for now 1 year. And each time the error is decreasing, right? And if I'm only doing this for 1 year, but for 5 years, but what you notice though is that regardless of the time, the central tendency bodes very well to the actual half fracture length estimate. So to me, I think to use this was you first train this model, you apply it to a production history, then you take the central tendency of that half fracture length across that production history, then you have a good estimate of half fracture length. So this can really be applied to what we call brownfield development, in the sense that you have some production history right there, but now you want to infer the half fracture length from an understanding of what's happening in the reservoir simulator that you trust. And then from there, you can go through and you can get an estimate of half fracture length. So using this understanding and just looking at the error through time, I saw this effect. So as I went through time, I saw that the error did increase. And so this kind of tells me that accuracy is optimized in early time data. So if you're a machine learning engineer and you're working on this sort of problem, it's probably best to kind of train a model on short-term data and not to use extended long-term data. And then finally, with that understanding, I went ahead and I moved on to actual transfer learning, right? So for transfer learning for half fracture length prediction, I generated a procedure to do the workflow, right? So the first thing that I did was I generated a new study. And within the study, I generated new sensitivities corresponding to hydraulic fracturing. And then, of course, I ran each of these realizations in this Monte Carlo study. And then correspondingly, and understand that as I ran each of these simulations, in a sense, I'm generating the source domain, in the sense of this is what I'm going to be using for transfer learning too. So I'm going to train the model on this source domain information. And then from there, I can apply it to that target domain. And in this case, the target domain is going to be the eager for production history, comprising more than 20,000 wells. So as an example of this process, these are the sensitivity ranges that I did for the Monte Carlo study, right? And these are the different probability distribution assumptions for the study. And these are the corresponding sample statistics generated from the study. And this is 2,000 realizations that I did for this Monte Carlo study. And so within that, these are the results of trying to train a machine learning model to predict half fracture length. So the same study as before, but now there are more parameters there. So this is not going to be a constant composition. But you can see here also that I've also excluded time, because in my previous study, I saw that time and rates were highly effective in predicting half fracture length. And I thought that there's going to be some sort of multicollinearity right there. So I didn't want to include that into the machine learning model. So I excluded time from the list of predictions here, because I think it's It was kind of almost cheating in a way, I guess. I thought it was redundant information, but I felt like the gas production did enough to kind of help in that prediction. And so finally, this is the machine predicted half-hour length from the Monte Carlo study, the expanded Monte Carlo study versus the actual data. You can see here that it's on the 45-degree line as before. I like to think does a great job at predicting what's going to happen within the simulator, right? And the error was less than 4 feet. So I thought that was somewhat reasonable to be used for, I guess, what you call the source domain machine learning model. So these are some summary statistics for the Eagleford. And I took that previous machine learning model and I applied it to the Eagleford and I placed it on a map. And I took the central tendency of those predictions across time and I placed it on this map. And you can kind of see the results on this map. So what this means, if someone's interested in performance based on previous production, they can kind of go through a similar process. They don't have to use our simulator. They can kind of use their own simulator, but they can kind of go through the same sort of process. Now with that, once I had the half fracture length across the Eagleford, I went ahead and I trained a new model to predict gas production using that half fracture length as one of those inputs. And when I did that and I placed it, I looked at the relative time, comparing the prediction versus the data, I found some really good results. It's almost like the results are history matched, right? And so I wish I can kind of show you the spot fire because I can go by county and by region within the Eagleford, and it can kind of shows the same story. But I do have this plot here that illustrates the cumulative volume by county, comprised from the data and also the machine learning model, which in this case was a decision tree. And you can kind of see here that it matches well with the data. So that's really the transfer learning study for half fracture length. Now, the next question I asked myself was, can I go and make a prediction out of location? In a sense, if I know information in one region, I train a model, can I take that model and apply it to another nearby region that's similar in the input parameters for that machine learning model? So within this study, this is the general procedure that I instituted. The first thing, of course, is collecting parameters and then applying the previous transfer learning model that I developed, but applying it to LaSalle County as the main county. And I chose LaSalle County was because it was the PBT in that area was very representative of an Eagleford. You know, you have black oils, you have white gases, you have, and you also have dry gases. You have other things happening there that are pretty self-evident within the county. If you look at the PBT distribution, so it's a great way to sort of train a model and test out this transfer learning workflow. So then using the area of interest, which is LaSalle County, I trained a machine learning model using half fracture length as a target parameter. And the reason why I did this was because I wanted to have a representation of the LaSalle County transfer learning in machine learning model so that I can apply it to nearby counties for the transfer learning study. And then for the area of interest, I trained using that input of that the half fracture length. I trained another model to predict the gas production for that area, LaSalle County. And then once I had an understanding of LaSalle County, I took those models and then I collected the information from adjacent counties. And this is really the focus of doing this was to test out the approach of transfer learning across the Eagleford. So and these counties that I chose were directly adjacent to LaSalle County from the east, west, north, and south. And then from there, I applied that machine learning model of half fracture length, trained on the area with no production history, which is LaSalle County, to make a prediction of half fracture length of the area with unknown production history, which is the adjacent counties. So in this workflow, I kind of illustrate the use of transfer learning. And then from there, just kind of going through and applying the gas production to kind of see how it correlates to the actual data. So this is the picture of the Eagleford. As I said before, the reason was because of of the PVT that I think is somewhat representative of the entire ether. As you see here, there is a PVT window for dry to wet gas to oil. And so I thought it was good that to try this on this county. And from there that I wanted to predict what's happening in Frio and Dimmitt, the county, and Bun. And these are the summary statistics of LaSalle County. Now, also note when I did, I made assumptions on the bottom hole pressure. Information is just not known really, but I just wanted to sort of illustrate the prototype for our counterparts in the kingdom. And so from there, this is the relative feature purportance for the gradient boost machine learning model for LaSalle County. You can see what's really driving the adaptation. And then applying that machine learning model, this is the half fracture length prediction across LaSalle County. And then now, when trying to predict the gas production, I trained a machine learning model for LaSalle County, and I used two models. The first model I used was a gradient boost, and the second model that I used was a deep learning model that comprised of 8 layers corresponding to 1024, 512, 256, 128, 64, 32, 16, and 18 units, correspondingly for each of the different layers to kind of illustrate a deep learning process. And so, doing that, this is the relative feature of affordance for the gradient boost and the corresponding and the machine for the gradient boost. And correspondingly, this is the same for the deep learning model. And both of these were somewhat kind of close together, illustrating the approach. And then finally, this is the LaSalle County relative time average this is the main county used to train the model for the out of place transfer learning model. And correspondingly, this is the cumulative volume estimate applying the transfer learning model of gas production and half fracture length to the adjacent counties. And these adjacent counties were Dimmitt, Frio, McMullen, and Webb. You kind of see the error in calculation. It's not as a good result as the prior transfer learning study. And I think this is where there can be some room for improvement. And so with that, then some of the conclusions I kind of pulled from the study was that transfer learning can be used to model shale gas performance, half fracture length prediction, and gas production prediction. But I don't think it's just limited to half fracture length. I think if you have a series of different properties that are unknown, and if you understand the physics and you have a simulator that can model those physics, you can pull this through the same process and use transfer learning because in that case, the domain task, the main domain data is coming from the simulator, while the task, the source task is going to be the simulator, while the goal is to model something that's happening in the field, right? So just having a simulator that you understand and trust can be a great way to understand what's possibly happening in the field. So you kind of translate those results directly to something that's happening in the field. And then transfer learning using production history results in history map parameters. I showed you those examples. I think that's really good results so far for a prototype. This is across more than 20,000 wells. If I did have the spotlight to show you, I can kind of show you by region the history match results, and it goes very well. And so I'm really happy with those results. And finally, transfer learning can be used to approximate gas production in undrilled locations. So what I mean by that is that you have an area that you know very well, and you can train several models to predict what's going to happen out of location in the nearby area. So some things that I think that I can add on to the study was to include more features. These features include corresponding to operations, more things describing the geology of the system, and also things related to hydraulic fracturing. Then, of course, I want to use a more robust finite difference simulator. The drawback, though, the simulator that's developed in-house in Aramco is very fast. It runs like, each realization runs less than 2 minutes. So it's really, really fast. So you can quickly run 2,000 realizations. If you use something that's more robust, like a finite difference approach, what happens is that it's going to take more time, right? And so that's the drawback of using the finite difference is that it takes a while to kind of get a good training set for transfer learning. And then finally, I want to apply the approach to the Barnett shell, Marcellus shell, and other shell plays in the US to see if these results can be repeatable. And with that, I will take your questions.
Thank you, Uchenna. It was an excellent talk. So we can open the floor for discussions and questions. Anyone? You can either send your questions in a form of a chat to me or in person, whatever you have. Go ahead.
Can you repeat that?
Can you repeat the question for the remote people?
Yeah, the person asked, did I consider a parent-child interaction? I didn't consider the distance between wells and the features, but that is something that could be added to the workflow. The way that I kind of considered it is that that I did have the corresponding effect of the parent-child behavior, which is the sudden drop in production. As you know, because as you remember, I did use gas production as a feature, right, for the high fracture length prediction. So in a sense, I kind of indirectly did incorporate some of the parent-child behavior by using the result of that parent-child behavior. Mhm.
How long has the
Yeah. Yeah. Actually, I had a similar project in my previous role at Devon. I can discuss with you how I approach that problem. But I see that challenge. It can be somewhat challenging. But there's some data science work you can kind of do. If you have your data, you can kind of go through the process of doing some filtering on certain aspects of that data to kind of isolate that parent-child behavior on some of those features, using those similar features. Well, first thing is that, you know, a parent is always older than a child. That's the first thing, right? So you can filter on that, on the age of the well. Another thing is, another thing you can also do is look at the effect on the sudden drop. Like, you know, we'll talk about all these advanced topics, but you have to kind of go to the old school. What's the B value through time for some of these wells, right? Are there sudden changes in the B value? Remember what the B value is, right? It's the change in loss ratio. What is the loss ratio? It's almost like a derivative of past production. So in a lot of sense, a lot of these things are inherent in what I call rate time data, right? So you can kind of use that approach.
Okay, Professor Dinderok has a question. Biral?
Yeah, hi. Thank you. Thank you for the nice presentation.
Mhm.
I was wondering whether you took like, I think you consider wet gas here, right? In all these studies, or any kind of fluid?
Yeah. I focused on the gas. So the
Yeah.
gas was the focus of the study.
Okay.
So I know in subsequent work, even up to now, we're considering a multi-phase approaches now. But for the sake of developing a prototype, I focused on gas.
Okay, because in that county, when you showed the properties, they were like oil to gas to all the way the full. So you only picked the wet gases, I guess, right?
Let me see.
Because the statistics that you showed, like LaSalle, yeah, in that one, if you look at producing gas oil ratios, they are like, you know, 588 to 1139. Yeah, producing gas oil ratio barrel per million.
Mhm.
I mean, those are
Mhm.
pretty high numbers, actually. I think they're like oil.
Yeah.
So did you, I mean, maybe you converted into equivalent, because I see gas gravity is like less than 0.55. Like, I don't know, maybe they are reported numbers. Maybe you converted them into gas equivalent.
Well, for this work, I did focus on gas. Let me see.
But those are not gas ranges, actually.
Yeah, they're not gas ranges. I did not. I did focus on the gas, but in the machine learning process, I did not include the prediction of oil rates and water rates and other things like that.
Okay, okay, that's what I was wondering. Okay, thank you.
I used the PVT information on hand for that area.
Okay, okay, I see now. Okay, thank you.
I think we have a question here.
Very much for the very next. My question is, currently, I'm working on soup storage in gas reservoirs, and at the end said there's the possibility for completion. There's a possibility of predicted gas performance on those locations. So I just want to know, what do you think is the possibility of predicted gas injection performance storage gas reservoirs?
Please repeat the question.
I think she was asking what's the feasibility of predicting gas injection performance in adjacent areas, right? For storage reasons. I think it's going to be tricky. One thing I think a lot of times with the gas cases that you have condensate blockage, right? That's a possibility. If you're injecting something, I'm assuming that you want to mitigate some sort of condensate blockage, or you want to improve some sort of performance, like enhanced gas recovery, right? And so I think in your training set, if you were to use a similar process, you have to make sure that your simulator can model those things first, right? As a sort of training, as a sort of a synthetic training set. And so I think for that case, you'll first have to get an understanding of the possible physics that can occur before you can model things that are out of place, right? Yeah.
A question about your training data set. When you talk about time, was that the time relative for each well?
Yeah.
So time from start.
Yeah, time from start to finish. Yeah, that's very important. Yeah.
And when you were ranking the relative importance, how did you do that?
This is a permutation of importance. It's like a typical thing you do in machine learning. It's a great way to kind of get an understanding of what's really driving a prediction. This is a calculation procedure you can use for any deep learning or machine learning model. I can sit down with you and discuss how I did this in Python, or how I did do this also in other environments. You know, the different tools I use are Python, or a lot of times also, I know it's not as popular, but I use ML.net. I don't know if you're familiar with that. This is like a way to sort of use Visual Studio and a C# environment to generate predictions. So. Yeah. A lot of times, you know, when you go through a data science workflows, you have to make the decision if you want to use certain parameters. The data that I used for this was sort of like a public data set. It had lots of information, but a lot of the information was missing. So I chose things that were kind of abundant in that data set as sort of features in this workflow. But it's possible if I had more data, more completion simulation data, I could use that information. What? Oh, ratio. Okay, so I used a third-party software to kind of do some of the training, and so this is the debate about auto ML, right? So a lot of times auto machine learning. So there are popular libraries out there that can do that for you, in the sense that instead of going there and trying to code every single possible model for your model competition. When I say model competition, comparing different models like, you know, gradient boost, random forest, deep learning, and etc. There are some auto ML libraries. So we have one that we use at Rank Americas that is very robust, called a data robot. I don't know if you ever heard of data robot before. It's very robust, and it's a great way to do training in the cloud, in a hybrid cloud, not a full cloud, because all the guys will believe in the cloud. Not allowed to believe in the cloud, but because we don't want our data to be out there like that. But this is a way to sort of get a quick understanding of possible different models they can use. And so to kind of answer your question, yeah. So initially I used like 64% for training, right? 64% for training, right? And you go through a model competition and you find those best parameters that perform well with a 64% for training, and then it's split between a validation and out of bag test. And then once you do that, then you up the amount of training and repeat the process using 80% training. You go through that same process of do that ranking to see what models perform the best. Then once you do all that, then once you're satisfied, you have to ask yourself, okay, let's go ahead and fully train the model and also calculate the cross validation, which is more like a randomized sampling of your full data set to see how well it performs. Your model performs on your data. So to answer your question, it goes from like 64 to 80, and then finally the full data set. So yeah, so it's like an iterative process for machine learning. And this is the auto ML that is used for the project.
Reason I'm asking is if that's possible to glean this kind of insight, possibly transfer this kind of learnings across basins as well.
Yeah. And so to kind of answer that, to repeat the question, I'm sorry I wasn't repeating the previous questions. There's a student here, a PhD student asked, are there inherent relationships that are found within the data that describe some sort of physics? Because we can kind of take those understanding of the physics and apply it to different basins. Sometimes you can kind of see it when you make a cross plot of the different parameters. Sometimes you can see different relationships that are apparent. One thing that I found a lot of times that people may not regard is that a lot of these properties are geospatially correlated, like porosity, thickness, and those sort of things. And so I don't think that you can really take that to another basin. Now, for the other parameters, you mentioned in the previous question about depletion and stimulation. If I had those parameters in there, they could probably be possibly correlated. It could pose some sort of physics. And so with that though, I think that's really where the transfer learning, I think, is hitting a hurdle. From the approaches that I've seen, in literature and other places and conferences, we're asking this question, okay, we have these different models. Why can't we take these models and generalize it in another basin? And why aren't those results so great? And so that's really the challenge, I think, as the next step for this workflow. For this, I can't say that I have all the answers for that yet, but this is something that I'm actively working on with other people. So, and possibly I can work with everyone here in Aim Deep. I think that's a very interesting topic, because if you have a full host of information for one full basin, and if you have another basin that's not fully realized in terms of data, I think that could provide a lot of value if you can generalize the possible performance in that area. There's one more question. Mm-hmm. Yeah. I went through a process of just like fine tuning, just manually fine tuning the deep learning layers. And so I found that would be somewhat satisfactory, the results. So there's some sort of hyperparameter tuning, that if anything, like the number of layers in the system. Yeah, but I did that individually myself. I decided to do like a sort of cascade effect where you sort of reduce the number of layers as you progress down the deep learning neural net. So.
Okay, I guess there is another question from Augustus.
Let me see if there's.
Augustus, can you ask your question?
Yes. I just want to find out the relationship of deep learning with multi-rate tests when we have production optimization schemes. Can we actually use machine learning or deep learning to predict these optimization values during multi-rate tests, especially with respect to increment in choke sizes?
Well, I can say like I've done similar stuff like that. I don't know if I'm allowed to share what I've done in that regards. But I think it's possible to do something like that to predict, I guess, like you say, choke performance, right? Is that what you're asking? You predict the
All right.
choke. I think as long as if you have a full data set, corresponds to something like a well test, if you have enough data describing your system, right? Especially if it's more than 1 million rows of information for a deep learning model, I think it's possible to make a prediction on choke performance. Now, the thing about choke performance though is that it represents a operations rationale, right? So we're talking about learning, right? So if company A choke management is something, it's like sort of corresponds to what they do, and you're trying to predict what company B is going to do, it's probably not going to be the same thing because company A has a different choke management strategy because of what's happening in their business, right? You know, so that's a challenge right there. But if you're trying to predict possible choke management within the same company, I think it's useful to do that. You can try to predict that choke management.
Thank you.
Okay, any other question? I have a general question myself, Uchenna, to basically be true to the name of transfer learning. I'm wondering if you have considered to take some general understanding of some optimum parameters for a particular field in some area, and then take that information with some minor modification applied to a nearby field.
Yeah, we are actively considering that. Specifically, you know, just taking what we learned in North America and applying it to Pacific areas in Saudi Aramco.
Yeah, and maybe less modification from one reservoir in a field to another reservoir in the same field.
Yeah. The main challenge with that is one aspect of this workflow or any data science machine learning workflow is the data. There's lots of data in North America, but a lot of times when you first open up a field in another part of the world, realizing that data is not there, right? So for example, I mentioned some of these features here, right? What if I don't have those same features in that new area, right? So that's a challenge. So we had to kind of come up with a sort of generalized strategy. Now I have some ideas about how to do this, because I think a lot of times we talk about developing individual models, right? To predict a certain number or to predict a certain task. But we have to remember that the people who do this, you know, the Googles, the Facebooks, the Netflix, the Apples, you know, they develop a lot of different models. And I still think there's room to use some of those models, but use it for regression purposes, not for categorical prediction purposes. So I think there are some opportunities, and I know there's some hungry grad students here who want to do that for us. And so hopefully through this partnership with AMD, hopefully we can generate some ideas around this, and it could turn to a useful project for us at Saudi Aramco.
So one thing I have learned myself from this inaugural talk is the future talks we will ask people who are asking questions in the auditorium to come to the front so that everyone can see them and hear them better. So this is my transfer learning to the next presentation that will be given by Ali Reza Shahin on some geophysical focused area. So with that, unless there's any other question, I'd like to once again thank Uchenna for giving an excellent talk, and I hope Since he has set a very high bar, I hope our future speakers will rise to the occasion. With that, thank you everyone for attending. I also want to thank Ahmed Ersahin, my PhD student, who has been quite active, as most of you know, with sending out announcements and everything. So, as well as all the staff at the University of Houston. Thanks, everyone. And we can adjourn the meeting right now.
Thank you.
Great.
Okay. So I'll talk to Uchenna in a minute.
Okay. Of course, it's on Zoom.